In this unit, we are going to explore some of the data analysis features that we have not yet explored. So if you go to the Data tab and the Data Analysis, in the last unit, we looked at these t-tests. And today, we're going to hit some of these other topics. Some of them are for more advanced statistical analysis, like the ANOVA, the F-test. We're not going to do them all, but we are going to talk about the parts that lend themselves to in sort of entry-level data analysis class. So first, we're going to start looking at correlation. And let's see, this is probably, yours doesn't have anything written here. So correlation we have done before, and we've made the correlation matrices. Recall, correlation is a number between -1 and 1 that measures the linear strength of two numeric variables. So the strength of correlation, I'm going to put measures linear association. Okay, so I'll even put here, it's between two numeric variables. You find the correlation between two numeric variables, not between, say, plate location and the strike ball, but our numeric variables in this data set are the speed in miles per hour, the speed in meters per second, the pitcher's age, and then the age to retirement. And so we have 4 numeric variables here. So let's go back to that data analysis correlation option. And we want to highlight those numeric variables. So I will highlight columns F through I. Now the labels are in the first row, so we get that. Let me show you what happens if you don't select that. And we're going to put the data in, say, I'll put it in L6, the output. Okay, now it's going to give me an error. Watch. The input range contains non-numeric data. Correlation deals with measures between numeric variables. And you're thinking, I did choose numeric variables, but these columns contain the label, the header in the first row. So that has to be selected, so Excel knows to ignore that. So here we have that correlation. I'm going to put it right there. Here we have the correlation matrix that we've talked about before. Let me just center these so they, whoops, so I can stand to look at them. And so this, we've made it manually before, but here it is, a correlation matrix. Okay, and it has the 4 variables here down the column and the 4 variables across the top. And then we have this matrix that's telling us what their correlation is. Now, speed, every variable is correlated with itself positively as 1. It's a perfect relationship. Now here, notice first of all that only half of the matrix is filled in. So that there's 1 on the diagonals makes sense, but only half the matrix is filled in because correlation is symmetric. The correlation of age with speed is the measure of the linear association between those variables. It's the same linear association strength if you say, no, I didn't mean age and speed, I meant speed and age. The linear association is the same. So whatever value this is would be up here. Whatever value this is would be over here. And so they don't need to fill in the whole thing. Now notice, let me just have these go down a few decimal points. Whoop. Okay, so notice that some of these numbers are positive and some of those are negative. Recall, a positive correlation means as one variable goes up, so does the other. So as age increases, so does speed. The correlation between speed in meters per second and speed in miles per hour is perfect because there's a perfect line that describes that relationship. Now this one is negative. As the age to retirement increases, the speed goes down. Because as the age to retirement increases, that means the kid is getting younger, and so their speed is going down. Okay, so the idea with correlation is to say, does it make sense to represent the data with a line? And so we have a rule of thumb that I thought I would put here. A perfect correlation is 1. That means the data is exactly linear. But if you have a correlation that is anywhere from 0.8 to 1, we're going to say that's strong. It makes perfect sense to represent the data with a line, which we will do in this next section. So if you have something with a correlation that is like, say, 0.6 to 0.8, well, then that's a moderate correlation. We can represent the data with a line, but we shouldn't expect the linear prediction to be super, super great. Now, if you have something with a correlation of 0.3 to 0.6, okay, there is a linear relationship, but it's not awesome. Makes sense to note the linear relationship, but to represent the data with a line, I would say is questionable. Now, if you have like data with a correlation of 0 to 0.3, that's saying, you know what, there's really not a linear relationship. Do not think that way. Now we can go the other way too, because this is as one variable gets bigger, so does the other, but you can have equally strong correlations with as one variable gets bigger, the other gets smaller. And so those are negative correlations. And so we'll just mirror the positive. And so here we'll add negative 0.3 to 0, which means we're going to go negative 0.3 to 0.3. So in other words, of course, these are perfect, although that's not very telling. These are correlations with themselves and with variables that are perfect linear derivations. So that's not really interesting. But we see the variable age and speed. Age and speed, whether it's miles per hour or meters per second, it's the same. It's a moderate correlation. So that's our like moderate. We'll note that. And so it would make sense to look at this data and make a line that represents the data. And we will do that in the next section.